Again, so we are on chapter 4, the last topic for our, we will have our uh, long exam. We will talk about alkanes and cycloalkanes, of course, for the nomenclature of the alkanes and cycloalkanes. They've learned that in the laboratory, and for most of the times, you are already familiar with how alkanes and cycloalkanes would look like in the three-dimensional levels. Now you've learned that there is an application where you can use and 3D models using some apps that you can view your alkanes, cycloalkanes in the three-dimensional manner. So nevertheless, we'll still introduce, we'll have a short introduction, the shapes, and we will escape on how to name alkanes, cycloalkanes, alkenes, and alkynes. We've learned that again in the laboratory. And we'll discuss on properties of alkanes and cycloalkanes, the sigma bond and the bond rotation, the conformational analysis, the relative stabilities, conformations of cycloalkanes, what are those? We'll check on what are the most stable conformations of our cyclic alkanes or cycloalkanes, not particularly the cyclohexanes, if there is substitution present, and how do we distinguish them for certain positions in the eggshell and equatorial positions. And then the bicyclic or cyclic alkanes, normal chemical reactions of alkanes, and how do we synthesize our alkanes and cycloalkanes. So that would be the highlight, but the last part will be the highlight. We have to look into the properties and then the reactions, chemical reactions. So of course, you know that alkanes and cycloalkanes are hydrocarbon compounds, and we can see that the only atoms or elements present in these compounds are the carbon and the hydrogens, and you only see carbon-carbon bonds. And if you review on chapter 1, you will see that for this carbon-carbon bond between the carbon-carbon bonds in alkanes utilizes the sp3 hybrid orbitals, and that it utilizes also the sigma type bond. So hydrocarbons you've learned in the introduction also in your laboratory that carbon-carbon double bonds, hydrocarbons are also called the alkenes and alkynes. You also learned that in chapter 2. And for those alkanes that are arranged in a ring, you call that cycloalkanes. And you have to classify further your cycloalkanes. Notice there is a possibility that there will be would have a general formula of the CnH2, and sometimes also your cycloalkanes can be cycloalkanes. You can see double bond within the ring. Generally, the alkanes would have a formula of CnH2n plus 2, and our cycloalkanes would be without plus 2. And this formula for the cycloalkane CnH2n is actually similar to the formula of our alkanes. Major sources of our alkanes is the petroleum and industry. We know that petroleum is a mixture of organic compounds, most of which are alkanes and the aromatic compounds. So sometimes it may contain small amounts of other atoms, such as oxygen, nitrogen, and sulfur containing compounds. And we know that some of the molecules in petroleum are clearly of the biological origins. If you look into some literature, most scientists believe that petroleum originated from the accumulation of the dead microorganisms that settled to the bottom of the sea and that were found in sedimentary rocks. So it's being made over years now with by extreme pressure and thousands of years. And this microbial remains eventually were transformed into oil by the heat radiating from the Earth's surface. Originally, it's accumulation of dead microorganisms. And you can read on this no on the chemistry of petroleum refining. We call the process of petroleum refining to be cracking. And the first step to the refining is call it distillation. In the laboratory, we should learn to perform the distillation process. And with the distillation, there are two types of the distillation process. You have the simple distillation and you have the fractional distillation. Of course, there are other modifications of the distillation. If you do under pressure, you can do the steam distillation or vacuum distillation. But for petroleum refining, they usually separate the different fractions of the petroleum because it's made up of different compounds into fractions, different sizes of hydrocarbons, and we need to separate that by the process called distillation. In particular, it's called the fractional distillations. And in fact, there are more than 500 different compounds contained in the petroleum distillates that would have a boiling point below 200 degrees Celsius. And it's a mixture of alkanes of similar boiling points. So there's a number of alkanes. It's really hard to separate, especially the differences in their boiling points are not that far. Mixture of alkanes, however, are perfectly suitable for uses as fuel, solvents, lubricants, and the primary uses of our petroleum. So we know that without petroleum, no, of course, that's our source of energy for our vehicles. Okay. When a mixture of alkanes from the gas oil, usually you have the carbon-12 fraction and higher, it's heated to a higher temperature. In the presence of a variety of catalysts, no, the molecules break apart and rearrange into smaller and more highly branched hydrocarbons containing 5 to 10 carbon atoms. This is what we call as cracking, or in particular, catalytic cracking in the presence of some catalysts. Cracking, no, from a very high number of carbon atoms, it will be cracked to a branch hydrocarbon containing only 5 to 10 carbon atoms. Called the process again is cracking. In the presence of a catalyst, we call it catalytic cracking. In the presence of heat, the absence of catalyst, which is heat, you call it thermal cracking. And alkanes with unbranched chains would normally have very low octane rating. Heard so much about this octane rating whenever you go to some gasoline stations or to gasoline stations. Octane rating is always indicated. The higher the octane rating, you know that lessens the cracking to your engine vehicle. So this is how fractional distillation of petroleum would look like. It depends on the boiling point. You can collect the different fractions of the petroleum. For gases, you can collect that at below 20 degrees Celsius, and you can collect hydrocarbons ranging carbon 24 and 20 to 200 degrees Celsius. You can collect hydrocarbons that would have carbon, 5 carbons, so 12 carbon atoms, and kerosene 12, 16. That's your kerosene. For fuel oil, which is much heavy, carbon 15 hydrocarbons would have a higher boiling point, and easily use catalytic cracking for this in order for us to produce our 15 to 18 number of hydrocarbons. Carbon 15 to 18 carbon hydrocarbons. Then you can have lubricating oil above 350 degrees Celsius, and the residue, you call that as an asphalt. So the lubricating oil usually above 350 degrees Celsius are usually used as lubricants. And the highly branched compounds, such as the 2,2,4-trimethylpentane or the isooctane, indicates that for this compound, no, it's made up of 8 carbon atoms. This one, 2,2,4-trimethylpentanes and isooctane. And this is the one of the standard with which the octane rating of gasoline is established. According to the scale, now this 2,2,4-trimethylpentane has octane rating of 100. And for heptane, the straight chain hydrocarbon, a compound that produces much knocking when it burned in the internal combustion engine. It gives a rating of 0. So the more highly branched with your uh, hydrocarbon is, your gasoline, the more smooth with the combustion no, in the engine. And that's why it would be nice. We will have our gasolines with a very high octane rating. You can see if you go to the gasoline station, the price will also be much higher. So this will be the standard no, isooctane to give a rating of 100 when you have a mixture of this in the gasoline. And just remember on the range of the number of carbon atoms per molecule that you can see for every range of boiling point fraction and the different types of the petroleum, from natural gas to ethers to solvents, gasoline, kerosene, gas fuel. The higher carbon 20 and higher, you can actually have your paraffin wax, your asphalts, and then you have your refined mineral oil. You can see this one sa inyong mga lotions, to inyong mga cosmetic products, your paraffin wax, you can also see that sa mga lotions. So that is for gasoline. Now let's look at the shape of our alkanes. You can see from this fraction, and these are examples actually of alkanes. That will be our chapter all about. You can see that the shape of alkanes is a tetrahedron. You can see here, for example, your propane here, you have CH3, CH2, CH3. Your carbon is bonded to 4 different group of atoms. And you can check on the hybrid orbitals that carbon would utilize. It would be the sp3. You have to remember on the electron configuration of carbon atom, the carbon atom will be 1s2, 2s2, 2p2. No? On the second energy level of carbon, there are 2 electrons on the s orbital and 2 electrons on the p orbital. And you know that for the p orbital, there are 3 degenerate orbitals, right? So you can just imagine that the shape of the s and the p orbitals of the carbon would form bonds with other atoms. The follow on the octet rule would be somewhat different. But we've learned from the experiments that the bond length for particular, for example, carbon, hydrogen, CH4, no, it's the same and can only be attributed, and also the shape can only be attributed to the type of the orbital that carbon utilizes when it forms a bond with other atoms. And for alkanes having formed a single bond with other atoms, it utilizes the sp3 hybrid orbitals. What does the sp3 hybrid orbitals means? No, this means if you review in chapter 1 that the carbon atom utilizes 1/4, 25% S character, and 3/4, 75% P character of the orbital of the carbon. And it produces actually 4 sp3 hybrid orbitals, and that is the one that's being utilized by carbon here, for instance, to form a bond with hydrogen, hydrogen here, and carbon, carbon here. Okay, and also it depends on the orbitals that's being used. So for example, here carbon is bonded to hydrogen, CH2 bonded to hydrogen here. So there will be an sp3 and S type of bond formation between carbon and this atom. So sp3 and S type of orbital of bond that's being utilized by these two atoms here. And when there is that head-on overlap to form a bond, you call that type of bond as the sigma bond. You review in chapter 1. And if there is the type of bond that would have an overlap that is sideways orbital, usually the sideways overlap will be attributed to the p. No, when the two orbitals, for example, you can review again in chapter 1, they would form a sideways overlap will actually form the pi orbital. We can see more of that when we see double bonds. And you can see also that almost parallel types of orbital, for example, you have your p or sp3 with a very high p character for sp3, which is 75%. There's also a possibility that they would also perform sideways overlap kind of bonding. Okay. So that will be the basis later we can see for the hyperconjugation. But that's side of it. Now we look at here that for our alkanes, no, you can see again that it utilizes the sp3 hybridization. You can utilize on the 3D models to check on the structure, and you can see that on top, you can see it's more like of a zigzag structure here. But of course, know that each of the bond angle when carbon or when the atom utilizes the sp3 hybrid orbitals would have a bond angle of 109.5. Okay. And whenever you have two types of two compounds, no, having the same molecular formula, but just the difference in the connectivity of the atom, we actually call them as constitutional isomers. For example, for a compound having C5H12, no, depending on the arrangement of the atoms, you can actually have different connectivity of the atoms, and it will lead to different physical properties as well. So for C6H4, for instance, now you have 6 carbons. You can have a straight um, carbon 2 is bonded to carbon 1, carbon 3 is bonded to carbon, carbon 3 bonded to carbon 2, 4 to 3, and 5 to 4, 6 to 5. No. This is a straight chain formula. You can have this, but you can also do branching on the second carbon and the third carbon, or on the second and third carbon. You can see that the total number of carbons is still 6, and the total number of hydrogens is still 40. Now, even if they have the same molecular formula, but this one, they're actually different compounds, and its physical properties will also be altered. For example, the straight chain hydrocarbons would have a higher boiling point as compared to a highly branched hydrocarbons here. The density also would also be higher for an unbranched hydrocarbon than the branched hydrocarbon. Same with the refractive index and also for the melting point. So the highly branched hydrocarbon would have a lowering in its melting point. And so the less branch hydrocarbon rather would have the highest boiling point. And why is that? Would I give a time delay? And you will see later on the properties of that will be attributed to the type of forces that would be involved, no, between this molecule and the other molecule of that. And see, you can see that you can see that there is no electronegative atoms in there, and then and with that, you cannot have an atom that would be partially negative, and you cannot see any dipole. So the only force of attraction that would be present between this molecule and other molecule would be due to the dispersion forces. Okay. So namings, you've learned that in the not gonna not gonna learn more of this. You learn this in the laboratory. But just know that we can classify your hydrogen and your hydrocarbon. You can have a 1 degree hydrogen, 2 degree, or 3 degrees. So let's say a 2 degree hydrogen that's bonded to carbon, it's bonded to two other carbons, and a 1 degree hydrogen is an expanded. In which this hydrogen is bonded to carbon that is bonded only to one carbon atom, and a 3 degree hydrogen atom is bonded to a carbon that is bonded to three other carbon atoms. And then the modifications of our alkanes, the alkyl halides, if you replace one of the hydrogens with halogens, you call that now as your alkyl halides. As to the naming, you've learned two types of naming in your laboratory. You can name, for example, this as chloroethane, or you can name with the functional ethyl chloride. Okay, so this is the substituted hydrocarbons. And you can also name by the functional class nomenclature. There's a common one. You can have the name by the halides, ethyl chloride, have the common alkyl groups, isopropyl, third butyl, isobutyl, yung pentyl, just have to familiarize with them. And then the last name would be the halide. So this is the functional class type of nomenclature. But you can have the naming in such a way that the longest continuous carbon chain, like for example here, you have your ethane and your substituents, the other atoms, the halo atoms will become your substituents. So for example here, ethane, chloro is your substituent and ethane will be your longest continuous carbon chain. You've learned about this in the laboratory. Do you have any questions? I think if you are to if you are to name, or most of the times when we do reactions or we do property and properties, no, it's really hard to write on the structure and draw on the structure. So sometimes in the quizzes or in the future evaluations, you will just be given with the name of our compounds, and then you will have to write the structure by yourself and predict, for instance, its properties or predict the chemical reactivities of the substance based on the name. It's much easier for us without writing on the structure, because normally when you write on the structure, you have to actually use an application to draw on the structure. So sometimes in the evaluation, you really have to write on the structure in order for you to see how the atoms are being connected to one another. Okay, and I think it's also included no, in the laboratory. How do you name bicyclic bicyclic alkanes? No, call this one as cycloalkanes. Recycle. Here is the your cycloalkanes. No, like when you name, you just have to add cyclo before your longest continuous carbon chain. Cyclopropane, cyclopentane, of course, know about that. The rest will be your substituents. But sometimes there are too many rings that you can see. For example, here, you can check 1, 2, 3, 4, 5, and you have 1, 2, 3, 4, 5. You can have 1, 2, 3, 4. How do you name this one? Yeah, because when you name this one, you have a bridge here, a bridge. You have a bridge here. You have your 2 bridge ring. You have a 1 carbon bridge, and you have your 2 carbon bridge here. So how do you name? No, so this one you call this one's the total number of carbons here is 6 plus this one is 7. So you call this one as heptane, but there's 2 rings. You call this as a bicycloheptane. So how do you name this one? So since it's a bicyclo, so you have 2 rings. Okay, you call it bi for 2 rings, and then you call it cyclo. And because there are 6 carbons, you call it heptane. So bicycloheptane. And you call on the number of bridges that you can see. So you can see that in this side of the ring, you can have your 2. You have this bridge before this and this and this. So it becomes a bridge. You have two carbons here, and this side of the ring, you also have 2 carbons. And here you have 1 bridge. So you actually have 2, 2, and 1. This one, 2, 2, and 1 is a bridge. So you call this, you name this one as 2 bicyclo, not parenthesis, bracket 2.2.1 heptane. So I hope you won't be confused whenever you can see this kind of namings. No, it only indicates that the cyclic, there are 2 types or more than 1 ring in the compound. For example, this one, you call this butane. So there are 1, 2, 3, 4 carbons of butane, but because there are 2 rings, so you can see, so you have bicyclo. And after the bicycle, you have to indicate how many bridge that you can see. So you can see here that there is one, there's no other bridge. You can see here, so 1.1.0 butane. You can see here, you can also use this one. You have 1, you can have 1 here. This one is direct connected, so there's really actually no bridge between the piece and ring. Okay, and so I'll write the structural formula, for example, of 7,7 dicyclone anyway, it's not included, but it's also good that you also be familiar with how we name. So 7,7 dicyclobicycloheptane. So heptane, you have 2.2.2.1. So you have to bridge and you have seven. So you always have to count like 6 here and 7, and this is the 2.2.1 kind of ring. And you have your 7,7 dichloro bicycle. You can have this one. Okay. To name your alkenes and cycloalkanes, again, you just have to end with in the structure, and you have to know where would the double bond be located. If it's in the first carbon, you have the 1 butane. If it's in the second carbon, you name it 2. Okay, so for example, here there's 6-membered ring here. The longest can be the longest continuous carbon chain that contains your double bond. And so that would be your parent chain. So you have your hexene, and the double bond is located on carbon 1, 2, carbon 2. So you have 2 hexene. And you can count on the left, from the left, or you can count from the right. And whichever would have the lowest locant, you will choose that as the name for your compound. Okay, so in this case, you have 2 hexene. And then the others will be, you have other more substituents. You also include that one. So here there is 2 ways of naming, indicate the locations of the substituents with the numbers of the carbon atoms to which they're attached. So for example, here 1, 2, 3, 4, you have 4 continuous carbon chain. So you have butene, and you have to indicate where is the in. So you have 2, carbon 1, 2, you have 2 butane, and the other one is a substituent, and you also have to indicate that. For example, methyl here is a 2 methyl 2 butane. The other way of naming is can also indicate the 2 before the in, or the locant for the double bonds. You can also have but, or a but dash 2 dash in, and you have methyl but dash 2 dash in, and indicate the 2 for your methyl here. Okay, so either it's actually acceptable. Kasi naglibog mo nga nung ihasakto nga nung paandahin. So if you are to contest, actually it's just the same, it's acceptable. Many older names for alkenes are still in common, so we have to remember them, like ethene. The common is ethylene, propene is propylene. The 2-methylpropene is isobutylene. If you are dealing with the number of substituents in cycloalkenes, you always have to go for the lowest locant. Okay, just familiar with the alkyl groups having the double bond, for example, the vinyl and the allyl group. Okay, give the APAC name. So sometimes when we will be asked how to, this is an example in the laboratory, but again, whenever we ask, it's just easier for us to give you the name, and it's up to you to write in the structure. And that's what makes things complicated, because whenever you're just given the name and cannot translate that into the proper, or the proper structure of the organic compound. So it really does to wrong interpretation. Okay. If you see a double bond, then you know it's an alkyne. There's a common name for that. So whenever you have your alkyne, you end with Y and E. First, but also remember on the common name, for example, ethine, common is acetylene. Okay. Pentine. The same with alkene, you have to indicate on the locant. So such as this, you can call your triple bond can be located on different carbon atoms, but whenever you see an alkyne that is located on the terminal carbon, you call it the terminal alkynes. Okay, so let's look into the properties of alkanes and cycloalkanes. This is the more important for the writing the structure, naming. You know so much of that in the laboratory, so here we'll focus on the properties and what are the reactions really that the alkanes and the cycloalkanes will have to undergo. So normally the physical properties of our alkanes, we know cycloalkanes, they are gases, okay, at room temperature, 25 degrees Celsius and 180 in pressure. The first four members of unbranched alkanes are actually gases, and higher than that, you expect it to be liquids from carbon 5 to carbon 17, and above that, carbon 18, you expect that to be solid. So if you are using, for example, mineral oils, I expect that one to be between carbon 5 and carbon 17. That's a kind of a petroleum source of alkane. And for the one that you use in the kitchen, your methane, of course, it's an alkane, it's a gas. And for paraffin that you usually use in your oil or cosmetics or mga haplas, no, that's very solid, more or less solid. No? See a lot of paraffin for that, you expect the number of carbon is actually 8 and above. Physical properties of alkane. So here you can see the graph is on the x-axis. You see the number of carbons, and the y is the boiling point here. The red is the alkanes and the white is the cycloalkanes. You notice this is increase in the number of carbons. The trend of the boiling point also increases, and the same with cycloalkanes. Okay. For melting points, similar trend also applies. It's increase in the number of carbons, no, the melting point also increases. No? So how you define the melting point? You notice here that the more negative, the lower would it be. So 0 versus negative 200 degrees Celsius. You expect the 0 is of a higher melting point than the negative 200 degrees Celsius. So the same interpretation as with your boiling point. The higher the number of carbons, the higher would be your boiling point in your melting point. Well, there are some instances, no, that the difference would not be that much, but generally the trend will be that as you increase the number of carbons, the melting point and the boiling points also increases. So how do we define our boiling point? So the boiling point is a temperature at which the vapor pressure above the liquid is equals to the atmospheric pressure. Okay. And we need to overcome certain energy, no? We need to apply a temperature to overcome certain energy between the molecules in order to convert in the liquid state into the gaseous state, into the vapor state. So this type of forces between molecules will be attributed to the intermolecular forces of attraction. So if you remember the different intermolecular forces of attraction, you have the dispersion forces, you have the dipole forces, you have the hydrogen bond forces, and you know which one of them or which of those would have a very strong intermolecular force of attraction. The higher the dipole, you expect that there is a greater force of interaction between the molecules. So you expect that there is a greater intermolecular force of attraction, and you need greater energy to overcome that. And if you need greater energy to overcome that, you need to overcome the force at the higher temperature. Okay. So you notice here that for alkanes, for a straight chain, for example, alkane like octane, so the molecular formula of octane is C8H8 2N plus 2. So 8 times 2, 16 plus 2, so it will be 18. You have 3, 4, 5, 6, 7, 8. 2, 4, 6, 8, and 12, 15, and 18. Okay, so as you condense this, or you have a different connectivity between the atoms into a more compact one, highly branched, you see that the surface area no is much less than here. So here you can see if you have another molecule of your octane here, if you have, for example, We have another molecule of this compound, thing. You can see that there is a very large surface area for the straight chain alkane. And the force of interaction present actually is not dipole-dipole because you cannot see any electronegative atoms here. So what happened actually is that there is a strong interaction, dispersion forces between this molecule and this, no? Because there is a large surface area that they can interact with each other. So the forces of interaction for dispersion forces is greater for octane than this highly branched constitutional isomer, the tetramethylbutane here. You can see that the forces of interaction also between this molecule and the other is also dispersion forces. Cannot see any dipole end, no? They cannot see that this end will be negative, the other will be positive. So there is only instantaneous dipole. That's the one only present in this type of molecule. And it's being induced in the presence of other molecules. What is being present is on dispersion forces. Okay. And if you have a highly branched molecule, what happened is that there is a lesser interaction between this first molecule and the other, for instance. And the forces of dispersion, the dispersion forces between the two molecules will be lessened. Okay, so the type of forces again I mentioned it's the dispersion forces. Because of that, no, you need only less energy to separate this, convert this into the liquid state, such that the boiling point for this is much lower than the boiling point for the unbranched alkane. So chain branching makes a molecule more compact, reducing its surface area and reduces also the strength of the dispersion forces. And this is the effect of lowering the boiling. The same with cycloalkanes also have a higher boiling point, melting points in their chain structure. Okay. Any questions? Okay, we'll ask you next time. We'll just finish our lecture and then okay, so that's for the boiling point. See the trend again that is increase on the branching, the boiling point decreases. For the density of our alkanes and cycloalkanes, um, you see the graph in the previous slide is the alkanes and cyclo. As a class, the alkanes and cycloalkanes are less dense of all groups of our organic compounds. Say less dense, now you expect its density to be actually less than the density of water at 4 degrees Celsius, 101 grams per ml. So you expect that for our alkanes, because it's less dense than water, you expect it to float. No? And as a result, petroleum floats on water. And for solubility, you can see on the structure that all atoms present are only carbon and hydrogen, and there are no negative atoms. You cannot see the end of our alkanes to to be in dipole, you cannot see an end which is partially negative. You cannot see an end which is partially positive. So there is no point that it can interact with our water, which is very polar. For water, you can see a very an end which is highly polar, partially electronegative, at the end that is partially positive. And because of that, no, there is no point of interaction between alkanes and water. And because of that, our alkanes and cycloalkanes are totally insoluble in water because of their low polarity, and there is no way that they can form bonds with water. Even if you can see your hydrocarbons to contain hydrogen, but that hydrogen is not connected to very electronegative atoms, so in our you don't see the hydrogen atoms in our carbon to be partially positive, no, because there is not much difference in the electronegativity. And because of that, your alkanes and cycloalkanes have very low polarity and they cannot undergo hydrogen bonds. And the good solvents for our alkanes, cycloalkanes are the benzene, the nonpolar organic compounds, the benzene, CCl4, the CHCl3, the chloroform, and other hydrocarbons. Now, this is the one that I mentioned earlier that you can see on the structure of our alkanes and cycloalkanes. It's all single bonds, and type of bond that is present is only sigma bond. Okay, and therefore the sigma bond overlaps by a head-on collision between atoms. Let's see. What is a head-on collision? Okay, so there's a head-on collision in the sigma bond. For example, the sp3 and the sp3 orbitals would have a sigma bond, and there is only a possibility that it would undergo the rotation of that bond. So, but if you look into chapter 1 again, you can see on the see on the structure. So what is a sigma bond again? I just have to repeat just in case wala pa man but this is very basic in organic chemistry. So for example, you have your sp3 orbital and you have your s orbital. So where would the sp3 and the s orbital comes from? So that would come, for example, if you have your methane. Your methane, for example, is CH3. So carbon is bonded to hydrogen. For example, here, carbon is bonded to hydrogen. And when they do bond, for example, here, your carbon, this is your CH3, CH3, sorry, CH4, your methane, no? Your carbon would form a bond with 4 atoms, for instance, here. So your four atoms of hydrogen, rather, hydrogen would have one electron, one electron, one electron. Carbon would have four electrons. You remember, it has four valence electrons, no? But when it forms and it utilizes its electrons in the outermost shell, like here, no, it would have two electrons in the s orbital and two electrons in the p orbital. And you can see that the energy between this s and the p would be somewhat different, and the shape also of the orbitals is different. So in order for it to have a uniform orbital, to a more stabilized bond formation with the other atom, hydrogen, no, it would rather utilizes the what we call as the sp3 hybrid orbital. So how does the sp3 hybrid orbital forms? The sp3 hybrid orbitals is being formed by first there is that promotion. There is that promotion of the s into the p orbital. Okay, when this one electron in the s orbital is promoted to the p orbital, then you will now have one one electron in the 2s and one electron each in the 2p. And this s and 3p orbitals will be hybridized. Now, if you remember on the shape, okay, you have here the s and the p orbital along the y, x, and z axis, and we have also the shape of the s orbital. When it hybridizes, it actually forms like a lobe here, where you have your 75% p character and 25% s character. Okay, 143 yeah. And this is now our 4sp3 hybrid orbital. So when it forms a bond with hydrogen here, it forms a bond by what we call as a sigma bond overlap. Now there is a head-on overlap. What is that sigma bond? The sigma bond is an overlap head-on. So for example, here you have your carbon. Let me see. Okay, this one, you have your sp3 and the s. When it forms a bond, they will just form a bond head-on, no front here. And you would form a bond, carbon-hydrogen bond, molecular bonding molecular orbital. So you now have a bonding molecular with this orbital, no, sp3 orbital and 1s orbital. It now forms bonding molecular. This type of bond molecular orbital is what we call as the sigma bond. So if you look at the sigma bond, you can assume an imaginary axis across this carbon and hydrogen atom, no? And there is this cross section here. You will see that in this cross section, you can actually rotate your atom here, no, along its axis. So that is the picture of our sigma bond. There is a rotation. There is a rotation around the sigma. And what's possible is that because it can rotate within its axis in the bond, no, the molecule can actually assume temporary shapes as a result of that rotation. And that temporary shapes, molecular shapes, is what we call as conformations. And each possible structure is called the conformer. And we can analyze on the changes or the energy associated when when a molecule or hydrocarbon undergoes conformations by the conformational analysis. So how do we associate that conformation? It's just like you as a person, you'd still be the same kung whether mo pungko ka, mo lingkod ka, mo stretch ka, mahigda ka, ampak ka na, are still you. And the same with our molecules, whatever the rotation that the molecule would undergo within its axis, and that have to remember there is no bond breaking process. Any temporary shapes, what we call as molecular conformations. And there is two ways of doing our conformational analysis. So what is conformational analysis, for instance? So imagine here your molecule, your CH3, So you have your carbon bonded to 3 hydrogen atoms, and you have another carbon bonded to 3 hydrogen atoms. Now, if you look at from this side, you look at from this side, no, this side, no, you have here the here. Okay, we have 5 minutes. So here you will have a dihedral angle of 60. No, if you look 60 between these atoms here, we can actually use the Newman projection formula to see how the rotation between this bond actually happens. No? So the carbon and the carbon here are bonded to each other through what we call as a sigma bond using the sp3 hybrid orbitals of the carbon atoms. No? And so you will see, can use a Newman projection. The Newman projection is like this. Now you see a triangular look a bond. You assume that the center, the, the point in the center is your carbon, and this carbon is bonded to hydrogen, hydrogen, and hydrogen. And this circle here, sa likod, is another carbon atom, Canisia. And this carbon atom is bonded to hydrogen, hydrogen, and hydrogen. Okay, so this is our Newman's projection. So now what you can see here, if you look at this way, there is a dihedral of 180 dihedral angle between these two hydrogens, kani and kani. So sa itong reference, this one. And this, you can see that ikan dira paingon diriya, kani, and this hydrogen atom, there is a dihedral angle actually of 180 degrees. No? And you change this rotation, you can actually change this no? Rotation to kani, balik kag mga 60 na rotation. Okay. You call this one as this confirmation. Parotate nimo siya og 60, you can have this ng 120, itong atunga is 60. Parotate nimo siya og 60, magtapad na si hydrogen and hydrogen. Okay, so this kind of confirmation of our, what is this molecule? The ethane molecule, CH3, CH3. Call this one as a staggered confirmation of ethane. And here is our Newman projection of our Newman projection of our ethane. Okay, and letter C, it's depicted here is a dihedral angle between this hydrogen here and adjacent niyang hydrogen. It's 60, the dihedral angle between the atoms. Kaning adjacent. But kung kani siyang hydrogen and this, the dihedral angle is. Again, this type of confirmation is, it would be nice na if we have a 3D model, but you can just imagine using the chem sketch and chem draw. You can actually draw and you can actually view using the chem sketch and the chem. I believe that you already learned chem sketch and chem draw, all other apps, 3D apps, not to view our organic molecules. This is how I mentioned earlier. If you rotate this by 60 degrees, like this, so magtapad na si hydrogen and the dihedral angle between these two adjacent atom would now be 0. Kani. Iparotate na tag 60, kana pa yung dira or kana pa yung dito. Magtandi si hydrogen and hydrogen here, and the dihedral angle would now be 0. Okay, and this, through the rotation between the kaninga bond, carbon-carbon bond, and there is a sigma bond utilized between carbon and carbon. Okay, so when you can see this type here, there is an eclipse confirmation. The dihedral angle is 0. And if you look at into the energy associated, which of this confirmation actually is much stable for our hydrocarbon, you will learn that this staggered confirmation when this carbon here, this hydrogen here, and this is 180. you have the staggered conformation is more stable than the eclipse. If you rotate it 60 degrees Celsius, no, the potential energy of this molecule actually increases. So it is less stabilized in the eclipse conformation. But if you continue to rotate it again by 60, you resort back to staggered conformation. So the more stable is the staggered conformation. Why is that? Now you will see that in the staggered conformation of the atoms, hydrogen actually atoms are situated very far away from each other. And because they're situated very far away from each other, there is less electrostatic repulsion between atoms. And for that reason, the molecule is much stable. Okay. And the staggered again is and the atoms are situated away from each other as possible, and there would be a lesser repulsion. Okay. And this 12 kilojoules per mole between the staggered and the eclipse is what we call as the torsional barrier whenever we rotate with respect to our signal. Okay. And you can also expand that to our butane. So our butane, you can have, instead of two carbons, you can have another carbon attached to these two carbons here and another carbon here. So how do you project that in the Newman projection? Again, you can have these two carbons here to be Canina center and the circle one, another carbon. And what is attached to this carbon is the CH3. What is attached to this carbon is another CH3 here. And if the CH3 group, bulky group, is away from each other, they are in the staggered conformation. And more importantly, they are in the anti-conformation. So this is also staggered. The dihedral angle between the CH and CH3 here is 180 degrees. And you rotate 60, they are in eclipse conformation. Okay, and you rotate again, they are in the gauche conformation here. So you rotate here to the left, that's an eclipse. You rotate again here, this is still staggered, but the staggered that is a gauche conformation. You can only imagine which among of this is the most stable one. So if you look at into the energy barrier, you expect which one would be, do you think, is the most stable? Anyone? Alves. Walay namin now. Okay. So that would be your assignment, not to check on which of these three would be the most. Message. The anti, yes, it would be the anti. Now, there will be less repulsions among the bulky groups of atoms, does not have torsional strain from steric hindrance because the groups are staggered and the metal groups are far apart, and it is the most stable one. Okay? And again, just remember that whenever we transform from an eclipse, there is a continuation from this, from a gauche to an eclipse to a gauche again to an eclipse. So you just have to continue. There is a repulsive force equivalent to 3.8 kilojoules per mole from the eclipse to the gauche conformation. Okay, and you can see that the most stable is the anti and the least stable is the eclipsed form. Now, when the CH3 and the CH3 would have a dihedral angle of 30. Okay, so that's all for today. And next meeting, we will look into the stereoisomers. And I'd like you to read on some materials on the reference material, the chemistry actions of the chemistry of muscle action. You can read that. And next meeting, we'll look at into the conformational onto the cycloalkanes product. Okay, so that's all for today, and see you next meeting. See you next meeting, and just I will have an announcement on our problem sets that will be available on our. So I hope that you learned something today, and I hope that you were able to indicate your attendance. So for the uh, picture, I mean, like, having a full screen here. And next slide, split screen. Okay. Okay, so see you next meeting and bye-bye for those who are watching so many so many people in one phone, and please indicate your attendance. Bye-bye.